Okay, so I guess we can start. Any questions from the previous class? Sure.
Yeah, there is one thing that I couldn't understand, and that's how we get to the center of K-space when we are like at one of the corners or somewhere at the K-space. So, assume that you are at the minus Kx.
Okay.
I'm sorry, plus Kx minus Ky, okay?
Okay.
So to move further, you have to have another phase encoding gradient.
So basically, whatever gradient that gets you the integral of kt dt. Integral of gamma bar g dt. Okay, so we'll see that in the slide. 1 second. So is that the question that you have?
Yeah.
Okay. Well, I think we should be able to answer that now in the slide.
It was related to one of the
problems. Okay. Okay. Good. I think we'll come to that in one of the slides, Mahmood. So, any other questions? Okay. I guess we'll continue. So. We'll start with the recap of what we did last time. It's a bit of material, so just briefly, we went through this imaging equation in one dimension. So the effective spin density rho x is related to the signal that you're sampling in time domain through the Fourier integral, and by variable substitution, your Fourier conjugate variables are x and k, x being the spatial domain variable and k is the spatial frequency domain variable. So realizing that you could actually replace k and x as with their vector counterparts, you can write this as 3-dimensional, and then in a Cartesian sense you can write it as kxx, kyy, and then kzz. And then this is the k being defined as the integral of the gradient, basically time integral of the gradient, essentially the area under the gradient waveform. So we were sampling the signal and Fourier transforming that to image space. So today's class essentially is going to talk about these details in terms of what you're sampling, how you're sampling, and how is the analytical signal that you actually the coil is picking up is being translated to an image. You're able to display that image. Anyway, so coming back to what we went through last time, we had basically encoding in multiple dimensions that essentially you are doing by sampling the k-space points. Essentially the image space corresponds to there's a corresponding k space, and you're sampling the values of the coordinates at each k values, and you're moving through the k coordinate space by applying these gradients. So essentially with the first gz gradient you're moving along the kz direction to one end, and then by applying the could somebody switch off these lights? I'm sorry, I think it's probably easier to see things. At least for me it's easier, actually it's quite too bright. Okay, that's good, thank you. So this is taking you through the kz, that's through kz, and then that's through ky by applying this and then this subsequently, so one after the other. And then essentially you are there. In fact, you can also think of the trajectory of simultaneously applying those two gradients to actually traverse this path instead of going this way and then this way. So taking the diagonal basically. So you're doing that through application of these gradients gy for a duration of tau y, and then gz for a duration of tau z, and you can vary your position in k space by either varying your tau or g, the amplitude, either way. And then once you're there, then along the x direction you can do a few things, but in what's shown in the diagram is basically first you're going through one end of the K-space, and then Mahmood. So that's how you're applying the gradient. So I mean, you understand, by applying those gradients you're moving through the K-space. So if you want to go back, you just apply a negative ky gradient, and then you're back to your region, to this point approximately. So if you apply a negative y gradient along this, just as a bipolar gradient, then you would just come here and then go back. That's it. So that's how you're traversing the K-space. And along the redirection, same thing. You applied the gradient and then you went to one end of the K-space, and then you applied the rephasing gradient. That's when you're reading through the lines. The data points of the line.
So after reaching here, the red arrow, how are we going back to the K00?
Well, in fact, that's a good question. So typically there are rewinding gradients. Typically there are rewinding gradients to bring you back to K0. Now, if you assume that your TR is long enough, then obviously there is no phase left for the next RF pulse. So there is no signal left for your next RF pulse. I mean, before you apply the next RF pulse. So essentially you are starting with a fresh K space that you need to fill in, that you still need to move through and then traverse, and you're going to the next phase encoding step, where you're moving through the next part of the next coordinate of the K space. So basically every TR, every repetition, every acquisition you're doing, if you assume that at the end of each TR there is no signal, then essentially every TR you're starting a fresh acquisition with regard to K space. So, but you're still filling the same K space to step by step. You can't instantaneously get all these data points, right? So that's why you're repeating your measurement. But then in each repetition, if you assume that there is no signal left at each TR, then there is no, you're now nowhere within the K space yet. So then next time you excite, then you're starting fresh, then you're starting at the center of K.
So you mean that in every TR we have the pi/2 pulse?
Right, yeah. So if you see the typical imaging diagram, okay, this is just to differentiate the, so we'll come to that. So let's just go over this. So this is your frequency encoding gradient, where the phase is being accrued as a function of time along the time axis, and here you're accruing phase, you're encoding. Both are phase encoding basically in the strictest sense, because both are basically gamma bar times g times t. One is delta g times tau, or the other one is g times delta t. So both are still, you're just sampling the phase, combined phase, vector summation of the signal phase as a function of either time or gradient step. Then we saw the slice selection. Then we looked at how we do that by using frequency encoding, by applying the gradient while simultaneously playing out the RF pulse, so that you can selectively excite only those frequencies which correspond to the bandwidth that you want to excite. So let's say that's your slice, and this is your center frequency of your slice. So you would be your center frequency is this, and you have a bandwidth related to your slice thickness, which is given by this equation, and then you apply your RF pulse. So how you define your RF pulse is your frequency spread, where you have the ideal frequency profile of your, or you can say excitation profile of your slice. You Fourier transform that, which is essentially the frequency content of your RF pulse that you want, and you Fourier transform that, you get the time profile of that, which is a sync, which is actually, although band limited, it's not time limited. In fact, it goes from -infinity to infinity. So you can't play an infinitely long pulse, so you have finite pulse, then you're making some, you're limiting your number of zero crossings, meaning the time you're playing out the RF pulse for, and how good of a profile you would get is basically a function of how many zero crossings you have in your RF pulse. So for a realistic RF pulse length, you would get something like this. Ideally, if you have an infinitely long RF pulse, that's what you would get. Okay, so we also saw the refocusing of this slice. Whatever defacing was happening while you were applying the slice select gradient and exciting the 2D slice. We basically defacing is happening from half the slice select gradient, so you're refocusing that. That's this part, and then this is your 2D gradient echo. You're applying these gradients sequentially, and so could you repeat that question? So this is where you are basically moving through K space by every TR, assuming that at the end of each TR you don't have any signal, which means that you're starting with a fresh excitation each TR with a pi by 2 pulse. Not pi by 2 in this case. Well, we have gone through all of the previous examples were pi by 2 pulses, but you will see eventually that not all experiments need to be pi by 2 pulses.
So here we start from where? From like
it's
0 and minus ky?
Well, typically what's shown here is first you go to minus ky and then you go to negative kx max and then traverse to positive kx max. So that's essentially your diagram. Okay. And of course, if you realize you're sampling the signal for a finite time, then the sampling time is related to your position, the minimum or maximum value of your k along the redirection at least. Okay, so you saw this. So this is where you're filling the k space, and that's typical gradient echo. Actually, we can learn a few things from this animation. Actually, it's been a while I took this off of internet, but I couldn't find the URL again for some reason. So I just put it, animation is from the internet, so which is out there. So anyway, so you can see when you're filling the outer part of the K space, you don't see much in the image until the point you're hitting the center part of the K space, when you actually start seeing some structure, right? So essentially that tells you that and as you go along, the finer details of the image get more and more apparent, right? So essentially, if you translate that, the outer part of the K space of an image has more of a finer detail information, high spatial frequency information, and the lower spatial frequency or the bulk contrast or bulk structure of the image is captured in the center part of the K space. So just remember that, and that becomes appreciation of that fact becomes important when you look at different kinds of artifacts. Anyway, actually one more point was the imaging time becomes ny times tr, which is the number of phase encoding lines times the repeat time in this kind of sequence structure. Then we saw the different trajectories, and the other example of trajectories, you can think of all sorts of algebraic combinations. You can play out your gradients in every which way and trace out different trajectories in K space, and each has its own advantages and disadvantages, but the fact that you can do that is gives you a lot of it's another added degree of freedom for different applications that you can use MR for. And this is the spin echo version of it. Essentially you just have the central RF pulse, both of them being slice selective RF pulses, and you have the readout structure. So all the gradient encoding, spatial encoding structure is after the pi pulse here, but of course you can also think of these being applied before the pi pulse. You just have to flip the sign of these gradients then. And then we saw that there is some dead time after the spin echo every TR. Typically the TRs are long for 2D spin echo sequences. So to fill the dead time, you can do multi-slice 2D imaging, and then by shifting the center frequency of each slice, then we encountered the importance of the or realization of the effects of improper slice profile, because you're applying a finite RF pulse to excite your slice. So obviously you have these side bands, so you don't want the next slice excited you want your signal, you don't want your signal to be corrected from the next slice. So obviously, so to avoid that, you either have slice gaps or you do interleaved approach of acquisition, which is basically acquiring every odd slice and then every even slice, or vice versa, either way. Basically, you're acquiring alternate slices. And then, I mean, in terms of, because all these relationships are linear in terms of the gradient and the slice thickness, you can realize what is the, in terms of the frequency difference between one slice and the other slice, what would it be? You can figure out that by just writing out these equations of what is the center frequency shift and then what should be the distance between them, etc. Then we looked at, we just basically extended the phase encoding concept to the z direction, which is called partition encoding in sometimes. It's essentially applying a step gradient to go through the z part of the K space, and in this case the imaging time becomes nz times the number of z lines times then y times dr. Okay, so that's a brief overview. Hope you have a good understanding of the 2D and 3D encoding. Any other questions? You guys came in late, so any other questions you could? Okay, good. So today's class essentially is quite a bit of signal processing math. I'm afraid I'm not that good at math, but I will try to explain the concepts as well as I can. So the key points that we're going to go through today is properties of Fourier transform. Few of them, there are quite a few properties, and they're quite standard proofs for them if you go to any signal processing textbook. And more importantly, however, we will be looking at sampling, because we are actually getting the analog signal from the RF coil, but then you're actually displaying a digital image. So there is some step of digitization in between, which is we'd have to understand how that is happening, under what conditions should that follow, or what conditions should that follow to reliably replicate the spin density that you're trying to image. So in that process we will come across discrete Fourier transformation, and then we will look at effects of finite sampling and windowing of your signal. So before moving on in terms of the signal sampling aspects, we will just go through a few properties of Fourier transformations. This is analytic Fourier transform we're talking about mainly. So there are a few listed here: linearity, duality, and then scaling of space, shifting of space, or either domain basically. Then symmetry, even odd symmetry, and then convolution, how that relates to in one domain versus the other. What's the effect of derivative, and how is the energy conserved between two domains of the signal, representation of the signal. Okay, so linearity essentially, as the name suggests, it's basically allows the Fourier transformation is linear in its process, that if you have two functions and you want to calculate Fourier transformation of the sum of those two functions, then you can basically linearly sum them up. And it becomes important when you're trying to analyze certain aspects of the obtained image in either domains basically. So sometimes you have an operation which is easier performed in the K space versus image space. So that helps in having this property helps certainly. So the other one is spatial scaling. In this case, it's spatial scaling is shown, the formula for, but you might as well think of this in terms of scaling of the K space as well. So you can look at scaling of this variable in one dimension. Let's talk about the spatial dimension as the equation is showing. Think of that as either shrinking or expanding your function essentially. Now when you do that, basically there is a corresponding scaling of your K space the Fourier domain representation of your function. And if you notice, the amplitude of that k-space transform also is scaled appropriately. So essentially, the energy of your function is conserved if you see this, but it also tells you that if you expand objects in your spatial domain, things get shrunk in your k-space. So you will see what I mean by that, but I hope that's apparent from this equation for you. I guess the animation is wrong. Okay, anyway, so the shift theorem, this is one of the most important ones that you would encounter. A lot of things that can happen in MR. I mean, we have always looked at the perfect world of, until now, uniform magnetic field, your sample gives you just a magnitude signal, the real part of the signal, there's no phase, so the picture is clear. But in reality, there are a lot of things that can deviate your signal from that picture. So in reality, your signal is complex. So you would see that complex signal is affected by quite a few processes of acquisition, and typically you will have certain phase effects. So one of the ways to understand the phase effects is to look at the shift theorem one. So if you have a linear phase in one domain, that essentially translates to a shift. Now, if we are actually starting in k-space or the time space where you're sampling the signal, so let's start from there. If you have a shift in that time signal that you're sampling, then that translates to basically a linear phase in your signal that you reconstructed. This becomes important when you look at if you have motion, meaning that when the object is moving, when you're actually acquiring the signal from. So suddenly one k-space line, the object is at one point, and the next k-space line, the object has shifted. So in spatial domain, the object has shifted. The effect of that in your k-space is going to be a similar effect as you see here, basically. So if you shift the object, then you would see additional phase effect. So by realizing that you have this additional phase term in the new k-space line that you acquired, you can correct for that motion and then still put back the object where it belonged. So that's one application of that. So motion correction. And the last part, first two parts are talking about the motion aspect. The last part, you will see the shift property is used in discrete Fourier transformation to be able to capture the center part of the k-space when you're actually sampling the signal. So we'll come to that at the end of this lecture today. So we talked about phase part. So we know the signal is complex. So when we're talking about phase of the signal, we need to understand one concept which is important, and you would see, you would come across that at some point in your MR literature, is phase aliasing. So what exactly does that mean? So you have this complex signal, you have the real and imaginary parts of the signal that you've acquired. So to reconstruct the phase, you're using the arctan to get the phase. Now arctan essentially limits your function, the value of the phase between minus pi to pi. So even if your phase actually is greater than minus pi or pi, you're actually going to be mapped back to this particular minus pi to pi domain. So that property of the phase domain is called phase aliasing. So you would see that phase aliasing is basically this dark and bright bands of phase that you would see in your signal, and essentially if you remember this relation, that this additional phase that you would see that you're seeing is the phase aliasing is basically this property of wrapping. Now now that we see this wrapping part, you see different amounts of bands in different images. Both are from the same volunteer. Why do you see different amounts of phase wraps? In fact, if you observe, these are linearly varying phase values as a function of space along this dimension, which means that essentially this is the function you're looking at, which means in turn that in the k-space of this signal, there is a shift in k-space, which means that when you sample the signal, your center of k-space, or basically your k-space got shifted by k naught. Now, in terms of discrete points, you can determine by looking at the number of bands here how many k points did it shift. So in this case, this is going from plus pi to minus pi within one field of view. So that means it's just one data point. And here, how many data points do you see? So the number of bands essentially will tell you how many data points of k space it had shifted. Okay, is that clear to everybody?
Now from the previous slide, when you say motion correction, I mean instead of the motion correction.
Right.
So will it, if there is a motion, it will correct the thing, and then image is displayed. So will it change the resolution of the image?
No, you're correcting the k-space line. Okay, so when you're reconstructing that, you're trying to put back the object where it was. So essentially, it won't affect your resolution unless you're doing some interpolation operation. So here you're not doing that. You're just correcting the phase of the k-space line. So unless you're doing any interpolation of operation, then you would have you'd affect that. So the aliasing part is clear to you. So essentially, it's coming from the tan inverse domain. Basically, that's the reason why you see the minus pi to pi limitation.
So that can you show the graph tan inverse? So it is varying from minus pi by 2 to pi by 2, right?
Pi is 1.414, right? Right, sorry, no, hold on a second. Yeah, you're right, I think.
Because tan inverse, range is...
Yeah, I think... No, it has to be minus pi to pi. This plot is wrong, you're right. So it has to be minus pi to pi. It's not pi, it's pi by 2, right?
Yeah.
Right, exactly. So I did the scaling improperly. I think I took this plot off of somewhere else. So, but essentially it is from minus pi to pi. So this should be 3.141. I thought it was, I misread that.
I think R10 will be a good result between minus half pi to half pi.
Yeah, because
so that's why we use that R10(2) function to apply both cosine and sine of phase to do the what's that called,
Quadrature
yes.
representation. So basically representing all the four quadrants. I mean.
R10 you only get from minus
half pi to pi. I see. Okay. Yeah, that explains. Yes, that's right. Okay, so
I didn't understand.
So basically the tan inverse, if you are only so you have two numerators and denominator, right? So you can map that in the first quadrant only, with meaning that the numerator is negative and denominator is negative. Let's say that will still be mapped back to the same quadrant. Versus if both are positive, numerator and denominator are positive, versus both are negative, they would both be mapped into the same domain. Whereas in the way, if you take arctan 2, it will be mapped into the right quadrant. So here you're just using the two quadrants for mapping your tan inverse. Whereas you can use all the four quadrants if you take the sign of your real and imaginary parts into consideration. So that's why it's able to map from minus pi to pi. Okay. Thanks. Okay, so convolution is another important property that you would repeatedly come across. Again, it's to do, so basically the property states that product of functions in one domain is equivalent to convolution in the other domain. So whichever domain you start in. it helps in terms of it's one of the important properties you would repeatedly use and try to understand a few concepts, especially when you want to understand effects of certain filters in K-space or in the image space, either way. So what is happening, for example, the effect of T2 decay when you're sampling the signal. So you have, I mean, all of the signal equations that we went through in the past 2 classes, we assumed that there was no relaxation when you were doing the spatial encoding, right? But if you remember, there will be e power minus t by t2 of overriding that signal that you are sampling. So what is the effect of that decay on your sampled signal, on your reconstructed image? To understand those, which is basically a product of 2 functions in the sample domain, which is the Fourier domain, you can analyze that by looking at, by either looking at it in the Fourier domain in terms of the product, or you translate into the different domain, transform that into the image space, and then do convolution to understand what its effects are. And also, it's you will see that we will be using this when we try to understand the effects of finite sampling and windowing. And then this is the symmetry property of the Fourier transform. If your object is perfectly real, then in fact the real part of the Fourier transform has this symmetry property, and the imaginary part is this. And you could use this property if the data more or less satisfies the condition that, let's say, your object is real in the sense that your signal is mostly real and that doesn't have any phase component. Then you can actually use this symmetry property to just collect only half the K-space and then reconstruct the rest of the data. So that's one property that actually is quite often used to save time when you're trying to do very fast imaging. Haste is one example where people just acquire half the K-space, and then and it's one of the bread and butter sequences for body imaging or for fast imaging, essentially. So that's very important to realize, but you have to understand that provided, that's why it says with conditions, provided the data satisfies certain conditions in terms of the symmetry. And partial Fourier is one of the algorithms that's used to reconstruct such data where you only collect half the K-space. For partial Fourier, you don't have the constraint that the signal has to be real. It can be violated to some extent. It can be used for complex data, but there are certain limitations to that as well. So the other few properties that we won't be going into detail, but you have, you may be using one of those during the course of this course, are duality, the derivative theorem. The derivative theorem is essentially an inverted V function that you're multiplying your K-space with. So basically you're amplifying the outer K-space and minimizing the lower K-space. So essentially it works as a high-pass filter. So you're suppressing the center part because the K value is lower. And if you see, this is what I'm talking about. Hold on a second. If you see this, so it's multiplied by K, right? So lower K values, whatever coefficients you have, they are suppressed relative to the higher K values, whatever coefficients they have, right? So that means that it is more or less acting as a high pass filter, suppressing the low spatial frequencies. Which is what you see in the textbook is the example where you will only see the edges of the objects and not the major intensity, the general contrast of the object. And then the Parseval's theorem states that the energy of your function that you are looking at is equal in both domains. And then this, so there are a few Fourier pairs. I think the first one is the most important one that we will be using in a couple of slides now. Is the delta function that we actually talked about, I think 2 classes ago. Is basically the it's essentially, yeah, I mean the definition is given there, of course. and then the rectangular function, which the Fourier pair, the corresponding Fourier function being the sinc function, the transform function, and I think Gaussian. I think this is also something you would come across in 1 or 2 chapters, I think.
So here we are using normalized way for the sinc function, right? We have like 2 definitions for the sinc function.
Right.
One is sine of x over x, and the other is sine of pi x over pi x.
Well, I mean, whatever normalization that you use. In this case, we are using the normalized one. Yeah. So, I mean, essentially, you're trying to represent that as a angular frequency. So when you try to do that, you introduce either angular frequency or time frequency. You try to introduce pi or 2 pi into the equation and normalize that sinc. So now I think this is the important part. Until now we have seen basically a continuous function that you're reading in from your coil, and then you're demodulating it, and then you have the demodulated signal. Now what are you doing with it? Until now we said we only treated with the analog function of that, basically treating that as the continuous function. Practically speaking, like we said at the beginning, we would have to sample and then digitize it basically to show it as an image on a screen. So first we'll look at what sampling function are we going to use. I mean, what is the effect of sampling on the reconstructed spin density. So first this is basically your sampling function. Initially we had the integral, which is basically the integral of rho x dx from minus infinity to infinity is equal to 1 at x equal to 0, right? So we're just changing that to its discrete form. That's why you have the dx is replaced by the dk. I mean, in this case we're writing this in k space, so you have the k variable. So dx or dk is replaced by delta k, and then the integral is replaced by the summation basically. So that can be written as such, and then if you take the Fourier transformation of that to represent what is happening, what is the image space representation of such a sampling function is this. Now if you use a few relations to simplify that, you will end up with this, meaning that this is a delta function which is repeating itself every 1 by delta k width. Okay, is that clear? Well, mathematics part in terms of the equation, I'm not asking you whether the derivation is clear, that you will take time I guess, but I'm just asking you the implication of this equation, is that clear to you guys? Meaning that the delta function is periodic in 1 by delta k in this case, right? Okay, so we will see shortly what that means in terms of just visually to appreciate that. We will use that sampling part, the sampling function or the comb function, you can say that because it looks like a comb if you just look at the impulses. When we talk about the discretizing the signal, we haven't done that yet. So when we're jumping to now. When we do the discretization, what is the relation of the Fourier transform that we would be using to get to your image space? In this, it turns out to be discrete Fourier transform. The equation of that is represented here, where it is limiting from minus n to n. So which means that we're not sampling the infinite function, we are actually limiting our sampling to a few samples. Meaning that you're windowing your samples. This is your sampling part where you're sampling at finite steps of delta k, and then you're windowing the number of samples, right? I mean, assuming you have the infinite length signal, let's ignore the T2 decay, let's assume the ideal conditions of very long T2, then you will have the signal forever. Of course, you can't sample the signal forever, of course, that's why we're windowing, that's what we're talking about here. So, the interrelationship between the step size and the field of view that you're imaging is given here. Don't worry, we'll come to that, why it turns out to be this in the next couple of slides. And then by virtue of the discrete Fourier transformation and windowing, you will see that the delta x is basically the number of samples that you have acquired times the divided by basically the field of view divided by the number of samples that you acquired is your reconstructed voxel size. Okay, so we will come to that in terms of how is the delta x size determined, or L relates to delta k. Okay, so and discrete Fourier transform also has the same set of properties as the continuous Fourier transform. So that's listed here essentially. This slide sort of summarizes what is happening right from when you acquire, when you look at the induced EMF. So your MRI signal is taken and it is sampled and then windowed, truncated from the and then that's what is stored. The discrete sampling is done by the analog to digital converter, and the sampling rate must satisfy a certain criteria for you to be able to reliably reconstruct the signal. So you have let's say a sinusoidal signal to actually and you can sample that. You can sample, let's say the sinusoidal signal is the period of that is 1 second, which means that you have the crest and the trough within 1 second. How fast should you be sampling that particular signal to be able to see and recognize that it's a sinusoidal wave? So if you just have 2 samples, you would see the 2 peaks. Okay, you can probably recognize that. The more the samples, the better it is, but minimum is of course 2 in this case, right? So, but what is that minimum number for a function that you're obtaining from your coil? That we will look at. If you don't meet that criteria, if you just sample 1 sample per sinusoidal period, then you won't be able to recognize that it's a sinusoid, right? So that's essentially leading to artifact, meaning that you won't be able to reliably reconstruct your spin density function. And by virtue of this sampling and windowing, meaning the finite sampling part, you will see that your spin density function in real space is actually somewhat transformed and represented when you digitize, when you display that as a digital image. And what is that transformation? What is happening to that signal in terms of the delta x signal spin density that you have from a given voxel or given location, and how is that being represented in your image, or as a function of, I mean, the modification is as a result of your sampling and your windowing. So that's just a prelude of what you're going to see, and this is what we're going to discuss here. So you have your comb function, which is your sampling, and in this case we're starting in the k-space domain, which is your time domain of your signal. So let's say your sampling interval between one sample and the next is delta k. Okay. Now you saw that when you take uk, which is the sampling of the combing function, the comb function, you Fourier transform that, you get this delta function which is periodic in 1 by delta k, right? So represent that visually. You have this in the image space, every 1 by delta k you have this impulse function repeated. So the separation between these 2 impulses is 1 by delta k, which we're calling, let's say, Lx. Okay. So you're multiplying this sampling function onto your S of k, which is your time sample function represented in the k variable. So that's your product. So So that's your product. And then if you Fourier transform that product into your image domain, essentially that's basically, this is product in K space, right? So that's essentially convolution in the image space. So that's ux, which is this convolved with your spin density function. Follow? Everybody with me on that? So if you're starting with a sinc function in your K space, that corresponds to a triangle in the image domain. Now you're multiplying the sinc by this sampling function or comb function, so you're getting discrete samples of that sinc, and you're Fourier transforming that, and which is essentially, if you look at this expression, is basically convolution of this with the sampling, the Fourier transform of the sampling function, which is basically a series of delta functions separated by L. So you convolve that, you have your object repeating every L. Is that clear to everybody?
So, sinc function is correspond to the rect function.
Right. Yeah. I mean, this is just one function example. This is just a sinc is an example function in your. No, this is not sinc actually. This is sinc squared. I'm sorry. This is sinc squared. My bad. When it looked like sinc, except for that there are no negative values, so it is sinc squared. It's not sinc. So sinc would obviously be rectangle. I mean the rect function, right? So this is the triangle function. That's the sinc squared. That's the Fourier transformation of that. Okay, so that's just an example function in K space and then corresponding image space, what it looks like. So you have your image space object convolved with your sampling function, which is periodic in every L, which means that your object that you're reconstructing is periodic every L. So now if, let's say, you're not sampling at the right, let's say you have your delta K smaller, meaning, well, in this case larger, let's say you're not sampling so often, let's say you're sampling sparsely, every 2 delta K you're sampling it, okay, which means that your L has become half L, and let's assume this width is L, which means that now your object is going to repeat every half L relative to the original length. Everybody kind of following me on that? So which means that your triangles here are going to overlap one another. So that is called magnitude aliasing. So which means that if you're not sampling your function at the right sampling rate, at a certain minimum sampling rate, you will have magnitude aliasing, meaning that you're, by virtue of the sampling itself, because you're sampling it and you're trying to reconstruct the object from these finite samples. Originally your function is a continuous function, now you're sampling it, so obviously you're not getting the whole function, you're taking finite samples of it. Now what rate should you be sampling to reconstruct that function reliably is what this cartoon is explaining. So if you sample it at a certain rate, which ensures that the repetition of your sampling function in the image domain is Lx, which is larger than your object, then you will be able to reliably reconstruct that object. If it's smaller than your object, then you would have an overlap of your objects, meaning that you are still reconstructing periodic repetitions of your object, but they are overlapping one another, which means that you won't be able to reconstruct your spin density properly. So this essentially is your Nyquist relationship. So this cartoon is explaining you basically what happens if you don't have a large enough L or a small enough delta K correspondingly. So L is certainly 1 by delta K, right? So if your object length is A, your L has to be greater than A, which means that your delta K has to be smaller than 1 by A, dimensions of the object, inverse of the dimensions of the object. So essentially you're repeating this But imagine that if these two copies are lying on top of one another, just overlapping a little bit, then you won't be able to make out what is what. And now you can figure out that it's a leg knee joint. But then if you have this overlapped one on top of one another, you won't be able to figure it out. Which means that, that's the consequence if you don't follow the minimum sampling criteria, which is essentially given by this L being your object size, typically object size or greater than your object size. Okay, so the Nyquist condition is basically ensuring or telling us what should be your minimum sampling rate be so that you can reconstruct your signal reliably, and that relates to your object size. Now we haven't limited our sampling window yet. We are still saying that we are only saying that you have this continuous function, you should sample it at a certain rate to reconstruct the object, and the reconstructed object turns out to be a periodically repeating function, right? We haven't really limited our number of samples yet, at least in our discussion so far. We'll come to that, but before that, let's translate what exactly the delta K versus L relationship turns out to be in terms of your imaging parameters, because that's all the more important, because when you're doing imaging, you want to make sure that your essential imaging parameters for your spatial encoding are gradients, right? You want to figure out, okay, how long should I be applying the gradient for, and how large a gradient should I be applying for doing certain spatial encoding. So those questions would be in turn related to what is your sampling rate and then your field of view. So these are the expressions that you would repeatedly be using essentially throughout your, if you're choosing a career in MR, this is your bread and butter essentially. You have to be very well versed in these relationships. These are, of course, I think that's enough said. So delta K R being here redirection. So we said 1 by LR, which is the field of view, is your delta KR. Now we know delta K is also gamma GR, gamma bar G, delta T. So relate that, equate those two. Essentially what you have is gamma GR delta T is equal to 1 by LR. Okay, hold on. Well, I think I should have written that down, but essentially just remember this, that LR times this gamma bar times GR times delta T times LR is equal to 1. That, you can, whichever way you algebraically manipulate it, just remember one expression, and then from that you will be able to kind of derive the other stuff. So bandwidth read, which is defined as your gamma bar times G, read gradient times your field of view, is going to be equal to your delta T. The inverse of it is going to be equal to your sampling duration. So basically, again, you can look at that as your Nyquist relation or manifestation of your Nyquist relation. If you have a band limited function, okay, so meaning that you have finite set of frequencies within your function, then you can, if you look at that frequency spectrum around the origin, you have minus bandwidth half to plus bandwidth half, right? It's going from, if you have a bandwidth of PW, or let's say B, the largest frequency is basically the frequency spectrum axis is going from minus B by 2 to plus B by 2, right? So your largest frequency in your content in that particular signal is B by 2. In this case, that is basically gamma bar times GLR times GR times L divided by 2. Nyquist relation from your signal processing theory, if people are familiar with that from that perspective, says that the sampling frequency should be twice the largest frequency of your spectrum, of your signal. So if the largest frequency in your signal is bandwidth by divided by 2 in this case, times 2 should be your sampling rate. Inverse that and then times 2 your sampling rate. So that becomes 1 by bandwidth is your sampling rate, which is delta T. Sampling duration. Sampling rate would be the bandwidth. Is that clear to everybody? Okay, good. So practically speaking, because when you're sampling, it's up to you, right? Whether you sample every 10 milliseconds or 20 milliseconds. If your duration of your sampling is fixed, you can sample as many number of points as you want in between. Meaning you can change your delta t. The Nyquist relation is only telling you the minimum. You can always increase that, right? So in practice, typically you actually oversample your in along the read direction when you do that in the MR system. So if your delta t, if from your experiment, from your Lx, which is your field of view along the x direction or the readout direction, your sampling delta k turns out to be 1 by Lx. Essentially, it is 1 by 2 Lx is what is sampled, or delta k by 2 is what is the actual sampling rate, and then you just, when you reconstruct it, you just throw away the additional data points.
So what is the point of it?
The point is that you avoid aliasing along the along the readout direction, right? If you sample,
So if we stick to the Nyquist rates, we should be fine.
yes, you should be fine. But typically, it is just as a safety measure for you. Let's say you chose exactly here, and then for some reason you have breathed, and then it has now become bigger. Let's say. Now, of course, your field of view is larger, then you will have some aliasing when at the point where your object had become larger than your field of view, right? So to avoid that, you would be able to, you would be able to avoid that if you sample it twice.
How do we know that which points we should discard?
That's basically taken care of by the system. Which points, meaning that if you're sampling at twice the rate, then you don't need the in-between points, right?
Okay, this is in the case that we assume that we keep to the, like as you said, to the original FOV or something.
Right.
If we need actually to use some of the points, so how should we know that which points are useful or which points should be discarded?
Well, that depends on which k-space lines were corrupted, right? If you have any corruption, if you're still limited, your field of view is still bigger than your object, then you don't need that oversampling. You won't be using that oversampling. Okay. Or I think practically speaking, what's implemented is you would still reconstruct. What do you call, so we haven't come to the windowing part yet, but let's assume that we have discussed that essentially if you have n data points along a particular direction, you will have n data points sampled along in the spatial domain as well, n data points in k-space and data points in spatial domain as well, right? Now if you're oversampling it, you will have 2 n data points. Now oversampling is actually not changing your voxel size, it's only changing your field of view, right? So let's say for some reason you have your object is larger than your field of view. You can use the 2n data points to reconstruct the image which has larger field of view, and then only cut the field of view and take your object from with your original resolution. That in practice is what is done. In practice, you will still use that data to, if you have a problem, to do that. Then either way, if you don't have a problem, then it will reconstruct the way it should be, right? If you do have a problem, then it will solve that in terms of your object being larger than the field of view.
Does it help for improving the SNR oversampling?
Unless you're using those points to in your reconstruction, it won't. And SNR has to do with the number of data points. You will see in chapter 15 why that is the case. It's actually a consequence of your Fourier transform. Essentially, your noise gets distributed to more number of points compared to smaller number of points. So you'll be gaining signal to noise ratio with larger number of data points. Okay, so we saw that in the read direction. In the phase encoding direction, things are a little bit different, like as we said in the beginning of the class. that the phase is being accrued as a function of your gradient step rather than time. So that's why things are a little bit different, but essentially the relationship between delta k and field of view 1 by L remain the same. Delta k is equal to 1 by L. Is that clear to everybody? So you saw the smaller step size. Every phase encoding step you're moving up along the ky direction. So if you acquire more number of samples, you're not changing your resolution. Sorry, you're changing your resolution, you're not changing your field of view. Essentially, if you're sampling more number of phase encoding lines, you're changing your resolution, not the field of view. That's basically evident here. So delta LPE, which is your resolution along the phase encoding direction, is LPE divided by n, so that leads to an increase in your resolution, whereas the LPE is basically this step size. If you're keeping the step size constant, it doesn't matter how many steps you're acquiring, your field of view does not change. Whereas the more number of steps you're acquiring, the higher the resolution you're having along the phase encoding direction. Actually the same is true. Well, yeah, things are a little bit different in the redirection. Okay, so now we're talking about finite sampling. So until now we've talked about a continuous function, you just sampled it, and assuming that you have infinite number of samples and you take the Fourier transformation, and you get a repeated replication of your object every L distance. To avoid aliasing, you said this is the minimum sampling rate that you should follow, and that's what we have gone through until now. So now because you can't sample the signal forever, first thing. Second thing, well, that's the main reason in this case. Now if you have a window, meaning that you're limiting your number of samples in the k-space, which is, in other words, you're multiplying your sampled function by a rectangular function, right? Everybody with me on that? So data truncation is nothing but you're multiplying your sampled function with a window function, meaning you're limiting your number of samples. So that's your original reconstructed object. Now the multiplication in k-space with a rectangular function is basically a convolution with a sinc function. Now this is a sinc function because you have your rect function in your k-space domain that you're multiplying to get finite number of samples. So that's essentially a convolution. So your object is getting convolved by a sinc function. So originally your object had a finely defined edges. Now because of your sinc function, these edges become smoother, which means that your limited sampling has a smoothing effect on your sampled signal. So even though your spin density has a clear boundary, because of this windowing of your sampled function, your boundary becomes smooth. Now how can you change that? Let's think about that for a second. So essentially that smoothness comes about because of the convolution with the sinc function, right? The width of this sinc function here is inversely proportional to the width of your sinc window. So the larger the sinc window, the shorter is the width of your sinc function. So the sharper the sinc function is, the more it resembles the impulse, which means that you will have a fairer representation of your edges, meaning that your edges would be sharper. So that's the motivation for sampling more number of points. If you remember in the last slide, we said if you sample more number of points along, let's say, the y direction, it's not changing your field of view, but it's changing your resolution. So why changing the resolution? Higher resolution is important, meaning that your window you're increasing your window size by sampling more number of points. You're not sampling within the same window finer points. You're sampling the same step size, more number of points. So you're increasing your window size along the ky direction in this example. Everybody with me on that? I see some blank faces there. You guys with me on that? No. Okay, so let me repeat myself here. So you're sampling n number of like k-space lines along the y direction by basically stepping through this, right? This is your gradient step size. All I'm saying here in this slide is that if you increase the number of steps, you're not changing the step size, but you're just increasing the step size, number of steps. That is equivalent to increasing your width or increasing your width of your rectangular function, or decreasing your width of your sinc function. So by increasing resolution or sampling more number of points along the k-axis, you will have a better and better representation of your object, of your edges of your object. So that is why high resolution is important. I mean, that's how you visually appreciate that a low resolution looks really blurry and you see these undulations, and they're essentially they're called Gibbs ringing, but you see that ringing artifact, and that ringing artifact is a consequence of this convolution with the sinc, because it has these sidebands, right? So it is the consequence of this convolution with the sinc function that leads to those bands in your low resolution image. If you immediately follow that up with a high resolution acquisition, you will see that those bands are, they're not appreciable anymore. They're there because your sinc function is still, you're still windowing your sampled signal, meaning you're still acquiring finite number of samples, so you will still have this sinc convolution, but then the width of your sinc is so small that the oscillations are happening over a smaller spatial scale, so you won't be able to appreciate that. So you will see a better definition of your edge when you have high resolution. Is that clear to everybody? Okay, so essentially this. Now there is a finer detail here that you need to realize. I have used a rectangular function which is shifted by delta k by 2. Now why is that? You will see in the next slide. But basically uk is your sampling function. So this is your analog function which is continuous. You're sampling that and you're windowing that. That this is all in k space. Is that clear to everybody? Then this essentially acts as a low pass because you can see that and understand that in whichever way you want, but the effects are apparent. So the Fourier transformation of this is basically this sinc with a phase shift. Due to this shift in the k space, you have an additional phase here, and you have the ux which is repeating every L being determined by 1 by delta k, and this is your spin density function which is convolved with these functions. Clear? So the reason why you are shifting your rectangular function by delta k by 2 is this cartoon essentially, or is this basically illustration. So if you have an even number of points, which is usually what you would sample when you want to do fast reconstruction using fast Fourier transform, that is essentially the reason why you are sampling an even number of points. And because you are sampling even number of points, you can sample it in two ways, right? So you have your sinc function like this. You can sample it in this way, where you're not sampling the center peak, but then you're sampling the two other points. Whereas you shift it by half delta k, and you're sampling the center point, but then the center is lying, let's say you have 8 points. The center point here is lying between the 4th and the 5th point, whereas here it's lying on the 5th point. Everybody following me on that? So you have a vector of 8 data points. Let's say you're sampling your sinc function with 8 data points, okay? So in the left scenario, if you're sampling it this manner, the center, the peak of your sinc is lying between 4th and 5th, which you're not sampling. Whereas if you shift it by half k point, then you're sampling the center part of the k space on the 5th data point. So essentially, your k-space runs from 1 to 8, or you can see that as -4 to +3, with 5 being the center. Clear on that? Now the advantage is that you're sampling the center part of the k-space, which is very important for your reconstruction using DFT. Fast Fourier transform. If you're losing your center part of k-space, then that DC value is gone of your signal. So the contrast that you see would be, well, the baseline intensity would be lost if you don't sample the center of k-space. So you will see, I mean, in other words, translating that, you would see some signal loss effects. What would look like signal loss effects if you don't sample the center part of the k-space. So that is why your rect function is shifted by delta k by 2, so that you're sampling the center part of the k-space, and you're able to reconstruct this reliably. So finally, we are coming to the actual expression of the discrete Fourier transform of your signal that is being sampled and windowed, windowing from -n to n-1. Delta x is your voxel size. So the number of data points you are sampling is 2n in this case, right? Everybody with me on that? So 2n, because it's going from -n to n-1. There is the 0th point, so that's total number of points is 2n. Correct? Okay, so this is the corresponding conjugate expression for the image space. Basically, you're doing inverse Fourier transform, and your voxel size is basically so this times well, your delta L. I mean, you can write this in any number of ways, but n times L, n delta L, n times delta L is your field of view, right? So delta L is your delta x, which is your spatial resolution in your redirection. The expression is given here, which again is a consequence of all the relations between delta k and L and n. So if you're sampling n number of points, your delta x becomes L divided by n, L being your field of view, n being your number of data points. So L divided by n is your delta x or delta L, your resolution along the redirection, or phase encoding for that matter. That relationship remains. And then in the case of phase encoding, this is the expression. You can derive this from the first expressions, following these two expressions essentially. Delta k is equal to 1 by L. But like I said, these expressions and the ones that I showed you in the previous couple of slides, those are, you cannot afford to forget those. That's essentially how you're doing your experiment. Without following those conditions, you will end up with artifacts which are essentially defined as a wrong representation of your spin density. So anything that, and typically artifacts are a consequence of one of these, I mean violation of one of these conditions. So in other words, by extension, it's essentially a violation of the Fourier relationship. If you're not following the Fourier transform relationship, whether that is the discrete Fourier transform aspect or the in terms of the continuous form, if you're not following that, then you would have artifacts. So motion is one example, right? So if you don't correct that, put the phase back for the k-space and reconstruct it, you will always have blurring in your image. So that's an artifact. And that's just a consequence of your encoding process. It's not consequence of particularly a discrete Fourier transform, but it's just the encoding process, which is essentially your Fourier encoding, right? Any questions?
So can we discuss about one of the homeworks?
We can try. What questions do you have?
Basically the same thing that I asked at the beginning of the session.
Okay.
That's the question number 10.7, I guess.
Yeah, I can get that.
Okay, I think. Emil?
Yes.
We probably will have to stop and then have to go to the previous slides.
If you want to go for the questions, it is fine. We can record this stuff.
No, we can record it, but it'll be forever. It'll take me forever to go to the first slide. Well, okay, that's fine. I guess we can always do that.
They just oh.
No, that's okay because I had something. Well, if we do that, then it will stop the recording. So. Try. No, it's okay. I know it does. I know it does that. So don't worry. Okay, so here we are. Okay, there we go. Mahmoud, what question do you have?
Yeah, actually, I couldn't understand, how on this scheme, we go to. That's not the question.
So no, hold on a second. Your question, if I understand that right, is that from one TR to the next TR. How are you going back to the center of K-space?
Yeah.
That's your question, right?
Yeah.
Okay. You can do that in two ways. One, let's say you have rewinding gradients, which means that here you have another dephasing, negative gradient, which should put back to your kx equal to 0. And here you have an opposite gradient step, which will put back you to your ky equal to 0.
Which is not, actually
Yeah,
visible or used in reality, right?
No, people do use it.
Okay.
People do use it. Okay. Now the other thing is that if the net phase at the beginning of your next RF pulse, after the next RF pulse, let's say, right? If the phase is 0 along any direction,
okay, is not or is?
Is.
Okay.
Then that means you're starting at the center of K-space.
Of course.
Right? So that, as long as that condition is satisfied, which means that either if your signal is going to 0, which means there is no phase, of course, at the end of each TR, or you're purposefully rewinding your gradients to get it to 0.
Okay.
Either way, you will come back to k equal to 0 point.
I see. So you mean that we have to choose a TR long enough to lose all the...
In some cases, not every time. So in fact, actually there is something called RF spoiling, which you could actually, by changing the phase of your RF pulse every TR, meaning every time you're applying, let's say every time you're applying your RF pulse along the x direction, okay? But you can change that. You can apply that along x and then y along x and y, so on, right? So you could, by changing the phase of the RF pulse, not the way I just told you, but in a systematic manner, and so if certain conditions are satisfied, which one of that is being that the phase of the spins is 0 at the end of each TR, then you will not start with a net phase in the next. You will not start with a net signal at all. The transfer signal would be 0 every TR before every RF pulse. Sorry, after every RF pulse, there won't be any transverse magnetization to give you signal. Okay, so meaning that the previous transverse magnetization created in the previous TR is not going to contribute signal to the next TR. So there won't be any. So you're starting with a k equal to 0 point as far as phase is concerned. Okay, so there are multiple ways you can actually make sure that the phase of your signal is starting from 0 at the beginning of the next TR.
Okay, so in that particular question, as there is no rewinding gradient, so we should suppose that the TR is long enough to lose all the...
Not necessarily, like I said, if you can, there are multiple ways you can manipulate the spins, right?
No,
So
there is no nothing mentioned over there that
now all the sequences until now, we are assuming that TR is long enough, much greater than TE, is long enough that the signal is decaying until now, and I think until chapter 15 also, we're still assuming that TR is long enough that your T2 star decay is going to lead to zero signal along the transverse domain. From chapter 18 onwards, you will see that that condition is not always satisfied. So to actually get to that condition, there are other additional things that you need to do in your sequence to make sure that every magnetization, you're starting with a fresh transverse magnetization with zero phase.
But for now, we can consider that.
For now, you can consider that the TR is long enough. Okay? Any other questions? Okay, so I guess, are there any other topics? I mean, I'm just trying to think if we missed anything. Well, I think we can, if I did, I will try to cover it in the next class, in the initial 5-10 minutes. Okay, thank you.